Okay, so participants, now it's time to introduce our next speaker, who is very special person who is coordinator of our FDP, material modeling for nano-electronic devices. He is the brain of our team. He is my mentor, who is motivator for many of young researchers like us. So I'm very happy to introduce to him. His title of talk is Modeling of Polymeric Materials, DFT Approach. The Sir, Dr. Mohan L Verma Sir, is the Professor and Head of Applied Physics, Sri Shankaracharya Group of Institutions, Bhilai, Chhattisgarh. Sir has got his PhD degree in year 2000 from Pandit Ravi Shankar Shukla University, Raipur, Chhattisgarh, in solid state ionics physics. Sir has more than 20 years of teaching and research experience. Sir has got various professional recognition, awards, and fellowships. On the guidance, by the guidance of Dr. Mohan L Verma Sir, Sir has established 3 research labs. First is Condensed Matter Physics Research Lab in year 2001 for material preparation and characterization studies and solid state electrochemical device applications, which is purely used for experimental studies. And next is for computational modeling, a computational nanoionics research lab in year 2012 for material, nanoionics material modeling and simulation to study electrical, optical, transport and mechanical properties of nanoparticles, nanotubes, nanoribbons, semiconductors, and etc. I am happy to share that this is the first parallel computing lab of Central India, which is collaborated with the Michigan Technology University, Houghton, USA. Sir has also established a sister research group in India as a Siesta India to work together in the field of nanomaterial science to study properties and device application. In this group, it is a free online training discussion session are encouraged to learn and study different material properties. Various MTech PhD students from all over India and from foreign countries also are availing the benefits of this group and lab to learn the material modeling for their projects. So he is a member of many professional groups and completed various projects funded by the government, and recently also Sir is the principal investigator of various projects going in process funded by the government and by our university also. So I welcome you, sir. This is your workshop only. I invite Dr. Mohan L Verma sir to share his knowledge and expertise with us. Welcome, sir.
Okay. So I think my sound is okay?
Yes, sir.
Visual, sound and visual both are there, okay? Okay, so good morning to all. Everything is okay?
Yes, sir, it is okay.
So good morning to all. I am Dr. Mohan L Verma from Computational Nano-Electronic Research Lab, Department of Applied Physics. Welcome you all in my presentation. The title of this presentation, it is the modeling of polymeric materials, and this is a DFT approach. So first of all, I would like to thank my supervisor, my guide, Dr. Rakesh Chandra Agrawal, and the mentor, Professor Ravindra Pandey, and Dr. Rodrigo for their support, their encouragement, and their guidance, their help, their blessings, and without which it is not possible to possible to exist myself in the field of in this research area. So I am very much indebted to all these persons. This is my research group, and my first student is Dr. Aarti Verma, and I have also mentioned that the research field. Actually, So far, you have learned numbers of lectures, either purely theoretical or purely experimental. And one thing I would like to mention here is I am the person which is actively involved in theoretical as well as experimental research work. So you will enjoy the combo of this experimental and theoretical as well as the mathematical modeling. So Dr. Arti Verma's work was the pure experimental plus theoretical, some software-based studies on same images of polymeric materials she have found. And Dr. Nirbhay Singh, experimental plus theoretical, hybrid electric vehicle based and supercapacitor-based studies. Dr. B.K. Rao, he has done that mathematical modeling and now involved actively in the DFT. Kamendra Sahu, purely experimental works in polymeric material. Dr. Rachna Singh, Dr. Rupma, and these two students involved in DFT-based modeling using Siesta. Durga Vancho is also done her PhD in experimental, and some parts of her work was are related to DFT. So these are the students currently involved in DFT-based studies. Rachna Singh, Dr. Rupma, Swati Verma, conducting the program, and the Harsha Verma, Tekam Soni. These are involved in modeling, DFT-based modeling in different materials, and other students which are directly or indirectly involved with me. I am not a supervisor or just guiding them. Mathematical modeling, Dr. B.K. Shora and Ajay Verma, they have completed their PhD in mathematical modeling, and experimental, Arti Verma, Nirbhay Singh, and Assam. And all total 80 students have completed their works, and three are working in this lab. This is my institution, Sri Sankaracharya Group of Institution, Sri Sankaracharya Technical Campus. This is the main gate of my institution, beautifully designed. And, it is always ready to welcome you. And this is NAC A-grade institution, and all the branches of this institution are NBA accredited. And, this is my Chhattisgarh, and I belong to this beautiful Chhattisgarh full of greenery, and my institution situated at district of Durg, and this is the administrative block and other blocks. My lab, my computational lab, this is the computational lab, and the experimental lab. Some glimpse I'm just trying to show here. So here I am using Siesta as a tool, and some other pre and post processing tools, and these are the experimental lab where the polymeric based materials are under study experimentally, and especially that electrochemical properties for batteries and supercapacitors devices. So the outline of my talk, first I will talk about some introductory part of the polymers, then the computational study. In computational studies, I will cover it's a DAS, BDAS, and charge density, and you all are familiar with these terms now. And but in context of the study of polymers, influence of this polyethylene glycol plasticizers and some salt doped PEO, and also I will discuss about the effect of molecular twisting on electronic and transport properties of some biomolecules as a concluding part of this lecture. So about the polymers, generally I will talk about the conducting polymers. These conductive polymer salts were firstly described in early 1970, and now it is very important part of this have very important applications in various solid electrochemical devices, sensors, fuel cells, etc. Out of all these conducting polymer polymeric materials, this PEO, that polyethylene oxide, this is the head of all polymers, and PEO-based solid polymer electrolytes were studied extensively in these years because of its a fast-hand transport, good compatibility, easy processing, and form of thin films, and also leak proof in nature. It has high crystallinity, this PO, and because of this high crystallinity, initially its conductivity is very low, and it's flexible, obviously, and subsequently its conductivity, ionic conductivity is initially very less. But in order to, when we able to reduce its crystallinity by adding some other salts, some surfactants, some other materials, when we dope, then its mechanical stability, mobility, and other things governs its better ionic conduction. So the most polymer salt complexes, cations should bind to the polymer chain instead of other ions, and it is really more to polymer matrix. So actually, here I would like to mention various experimental as well as theoretical studies have been performed and continuously performing, where materials are prepared and studied. Materials are prepared and studied by using different tools. So there are several methods of preparation of materials, and for the characterization, especially experimentalists use XRD, SAME, and FTI type devices to just to know why after doping salt and after doping some inert nanoparticles, the PEO, that polymer, shows very good conductivity, which is applicable, which is good for its application. It's used in various batteries, supercapacitor type electrochemical devices. So and theory, as far as the theory is concerned, it is mentioned in some theoretical paper that when we dope this salt, when you use plasticizer, that the chain, polymeric chain, disturbed itself, and there is one free volume theory there, where that ions move in between that polymeric chain when the volume increases. So it that particular ion, that in case of AgI, when we dope AgI, then Ag ion is free, and it is free to move in between that polymeric chain. When we talk about that lithium ion or sodium ion, then that lithium ion and sodium ion are free to move. So if that particular ions get space or free volume, then it can move freely, and the conductivity enhances. So that interaction, some theory also shows that the interaction between that ions and the oxygen part of this PEO, this takes place, and there is one Hoping model that by just jumping from one oxygen to another oxygen, that lithium and sodium ions, or that other silver ions start moving, and the conductivity enhanced. So this is the basic mechanism related to conductive enhancement of this PEO and PEO based solid electrolyte. So this is the motivation of our study. Purely experimental study have been done, and on the basis of the result, this type of theory are given, and one can get the details in literature. And also the changes is observed in bond length by using that FTIR. Crystallinity, it is studied by using XRD, and that if it is a form of any film, then the surface structure is analyzed experimentally by center. But now in this DFT based study, which we are performing in our lab on polymer, we try to observe all these mechanisms, all these phenomena on our computer screen by using computer experiments. So what we do, I am just giving a brief of that methodology we use in our laboratory. We design polymer PEO by using Avogadro and get its XYZ file, and then we just generate one simulation box and optimize. And for that, obviously, we use Siesta, and in some studies, maximum studies, we use that ZZA, generalized gradient approximation, that has a correlation exchange function. and double zeta polarized basis set we use. And then the system is relaxed by our method of optimization up to the force in each component, that is less than 0.001 electron volt per angstrom. So this is some output after optimization of the system. So we have actually limited computational facility, and in available computational facility we optimize just a PO with 5 oxygen. In one of the paper it is mentioned in literature that if that numbers of oxygen available in PO chain, it is if more than 5, then the result that will be good. If someone perform its molecular dynamic simulation or that DFT type study, then that's why we select here as a PO chain where that number of oxygen available, that is 5. So first chain here, this is PO5 with 5 oxygen, and in the second figure we just dope this silver iodide molecule and optimize the system. And then again we also try to increase the numbers of this polymer chain with this is two polymer chain, and this is the optimized structure, and these are just relaxed form. This is represented as PO10, and when in 5 in the first chain PO5 we are doping 1 silver iodide salt, and for that 2 chains, parallel chains, we are doping that 2 AgI atoms. That's why this is named as PO10 AgI2. And when we increase that numbers of AgI molecules, then this is that. Because in experimental part also, what we do, we first perform the composition variation by taking a different ratio of that PO pure and silver iodide in molecular ratio, and we get one optimum conducting composition by taking this. So here also we tried the same, but we have limited computational facility, so our studies were limited to this PO10 AGI file. And what we are observing here is when we dope AGI, its bond length as well as we observe the change in its bond length as well as band gap. So this is our charge density plot, and what it is observing here, this is partially ionic and covalent bond. As far as that silver iodide is concerned, it is purely ionic, but when we dope this, then this is partially ionic and covalent bond, and this is for that PO10 and AgI4. So this is a charge density plot. Now this is DAS plot, projected density of state, PDAS plot. This is for pure PO, PO5, band gap is maximum. When we dope that AgI, when we dope this AgI, its band gap decreases, as well as one meet keep state at center here, it is observed, and this is for the PO10, pure PO10, and when we dope that silver iodide, then the same effect is observed, but the changes what we are observing here is the change in its Fermi energy level as well as forbidden energy gap decreases as we go from this diagram to this. When we have this doping silver iodide is in 4 molecules, then that band gap, this is reduced up to 0.1 electron volt. And we are now trying to detail it, presently why such type of variation is observing, and since because of limited computational facility, we limited up to this, and further we will study at higher numbers of chain as well as higher numbers of salts also. So this is the DAS and forbidden energy gap also showing the same with that PO10 and 4 AgI is here, and So, as conclusion, by increasing the numbers of silver iodide molecules, the forbidden energy decreasing gradually, and finally becomes zero when we are using AGI as 4 molecules. And then electron doping nature of silver atom is gradually increasing, and hence the concentration of cation is gradually increased. And due to this HSAB principle, this is hard-soft atomic base principle, which actually are related to the interaction between positive and negative ions, the mobility will also be increased, and finally the ionic conductivity of polymer system is increased. This particular study, this has been published in Polymer Bulletin. And now the second part, where in place of silver iodide, we shifted to sodium iodide and lithium iodide, because at present that lithium ion conducting battery and sodium ion conducting batteries and the related electrochemical devices are in picture and abundantly used in our daily life appliances. So we tried the same study for this lithium iodide, and by using the similar methodology, we first take that PO5 and optimize this, and then we dope this lithium iodide salt, and clear-cut interaction of this positive part of this salt. It is with ion, that oxygen, it is observed, which is just analogous to whatever that theoretical studies are showing. That the positive part interacts with this one oxygen, and the neighboring oxygen interact this lithium ions, and that by hoping this lithium starts moving and conductivity increases. So we are observing the same for sodium iodide also, with this numbers of similar numbers of that polymer chains increasing, and similar behavior as we have observed in case of silver iodide, we are observing in case of that lithium. And since because of this lithium, the size of this lithium is less than that size of that silver ion material, so obviously its conductivity will be much more, because it requires very less space to move. So path is easily available for the movement of this lithium ion or sodium ion, so its conductivity will be obviously more than that silver ion conducting solid polymer electrolyte systems. So this is for the PO with the PO10 with 2 lithium. This is with the PO10 with 2 sodium iodide, and then again we further proceed to same with 4 lithium and 4 sodium iodides. These are the charge density plot. Obviously, it's also showing that partially ionic and covalent bonds. And, the parallel study. So the PDOS plot is here. So this is that P dot in absence of that salt, and in presence of lithium salt, and in presence of sodium for PO10. And with PO10, these 2 lithiums are adding, 2 lithiums and 2 sodiums are adding, and the further similar behavior, that band gap is decreasing, it is shown here. So this is the forbidden energy gap, binding energy also calculated. So in order to calculate this binding energy, the same formula which that computational for the computational studies we use, that that binding energy can be calculated is with this energy with PO plus salt minus energy of that PO plus energy of that salt. So this is that binding energy. Bond breaking energy we also calculated. And in first time, we have studied the mechanical properties of this polymer chain by using this DFT based theory. Then this is the beauty of DFT. Then we can play with each and every atoms of our system. So what we do in to calculate this bond breaking energy, when we just pick one oxygen or one carbon atom and start stretching, pulling it a particular direction, and up to that level when that bond breaks, and that the energy that when just bond breaks, and that equilibrium energy means that optimized energy of that system, the difference is represented as the bond breaking energy. And this study have been published in one of the journals, that Ionics. Same studies when is performed in this lithium chlorate. It is doped with that PO chain. So here again, that lithium is attracted toward this oxygen, and we have used this lithium LiClO4 for our further transistor-based study in light emitting electrochemicals, and this has been published in chemical physics. This is the plot for bond-breaking energy calculation. So the center point is, this is the equilibrium one, and one can compress that polymer, one can extend that polymer, and that effect can be seen. And here, the bond-breaking energy in electrode when positioned at 2 atoms decrease from the equilibrium position. So in case of this PO, pure along x-axis, y-axis, and z-axis. So what we do? So obviously here again, we have used my latest optimization script. Just I take the coordinate part, not that lattice vector part, the coordinate parts. I just take the coordinate of that oxygen and shift that oxygen and that x component at a part up to a particular level, from one positive 5% to negative 5%, and that along y-axis and along z-axis, and corresponding energy is calculated. So since that system that was aligned toward that z-axis, and that energy, that bond breaking energy, it is very less in case of that pure PO, as well as that doping of this lithium ClO4. So this bond breaking energy is, can be calculated by DFT also, and first time in my group this has been performed, and so that. Now the second part of this presentation, that is the influence of plasticizer in that PO and sodium iodide composite. So that PO and sodium iodide composite, the DFT study has been performed, and when we took that glycol plasticizer, then what will be the effect we have observed by using this DFT. And in this work, Shivani from Bundelkhand University is involved with me, and she did a wonderful job and performed all the DFT-based calculation. And recently we have communicated this paper. So just I will show you some result, and I'm not going to the detail because it is unpublished one. So obviously the method is same. We optimize this PO salt already optimized we have, and then we optimize this PEZ, polyethylene glycol, and then PEZ with the sodium iodide system with this 4-hour optimization process with a different basis stage taken as DZP and ZZA, that the correlation function. This is the optimized structure, the PO, and this is the PO5 with the sodium, and then with this glycol, and this in this glycol we have taken 6 atoms of this 5 and 6. This actually gives the numbers of oxygen available. And now this is the homolumo plot, and for this homolumo plot we have used Argus Lab tool, which is actually window-based tool. So if you have the structure form, then you can plot that directly the distribution of electrons in form of positive or negative. So in homolumo plot, one can perform easily there. So this is that homolumo plot of PO, and the band gap is this. This is in presence of pure sodium iodide. And now the PO, PG, sodium iodide with this gap, and the band gap obviously decreasing up to 306 electron volt in presence of that plasticizer. So this is the projected density of state, and the charge density distribution. And also we have checked that the breaking energy. I'm not showing the details here, what is the result one, but we have observed a good result in the presence of plasticizer, and whatever that experimentalist observed in their experiment, similar result we have observed here. And also in the detail, when we use that plasticizer, it's just interact PO chain and try to create some space, and the volume increases, and it also gives some extra space, extra tube type space to move that ions, and the ion conductivity increases. So this is that effect of the plasticizer. So now the third part, recently running in my lab, and one of the student from Pandit Ravi Shankar Sukla University Basic Science department is working in this. Here we have used one biopolymer, that is the Chitosan, and one of my PhD student did her PhD on this Chitosan based materials. So details DFT based study have been performed by her, Dr. Upma, and now Hemant Kumar Sahu is involved in this particular work. And what we are doing in this work is we are just taking that Chitosan and trying to twist it and observing its behavior. So that's why this is the title is given at the effect of molecular twisting and in electronics and transport properties. It is under study, and we have taken two molecules, two monomers, 3 monomers, 4 monomers, and try to twist its one monomer in a place, and observing some good result. So here I am just showing the result related to 2 monomer, and this is also in the stage of communication. So this is the different angle of rotation of 2 unit monomers. So this is one monomer, this is the second one. When we twist it with a different angle, its band gap changes. So initially its band gap was more than 2.5, and this x-axis, this gives the angle of rotation, and in the range of 15 degree we are rotating this. So it's start decreasing and they become almost constant here, and this is very good shown in 3 monomers and 4 monomers also, and in case of 2 monomers some discrete type result is showing, and it reduces up to 0.5 less than 0.5 electron volt, means its behavior is changing from insulating to conducting when it's rotated up to 175 degree. So this is the dust plotting, and also we are observing the drastic change in its band gap in the rotation in this one, and the previous plot is related to the band gap, and this is the projected density of a state for the 2 units of Chitosan. And we also performed that transistor bed study. So this is that homolumo plot, and the distribution of positive and negative ions are observing here in this beautiful figure. So this is that system, which is 150 degree rotated. Now the stability. So when we rotate that particular monomer, then its total energy as well as cohesive energy and formation energy, these are almost stable. There is not a remarkable change. But when we rotate it more than 135 degree to this 180, then we can observe the change in its stability also. So this is also one noticeable result. So in the next stage, we have performed the transport properties, and here we have used a transistor, and today we will in the lab session we will discuss how this transistor work, and yesterday Professor Pandey has given details of its theoretical part, and now its experimental part will be covered today. So that when the angle of rotation is less than 90 degree, then the current in the reverse biasing, it is in the order of 10 to the power 6 into 10 to the power 7. When it's more than then, this is at the forward biasing, its result is good enough. So why it is so? We will discuss in our next paper. And just showing here the glimpse of that. So as a conclusion, the geometrical optimization indicates reduction in crystalline nature of the polymers and increase in interchange separation, creating free volume. So we are supporting that free volume theory to enhancement of that conductivity of that polymer by this theoretical study. And DAS and PDAS obviously provide about the contribution of different orbitals and the formation of bands. And hydrogen bonding, this is also seen in charge density and more amorphous domain in complex due to this miscibility of PEG with PU. And the bond breaking energy for different polymer system, it is illustrated, and this is actually weakening that COC bonds. And the finding provides an avenue that the present polymer system, this is for the PEG system, the polymer kind to be used in electrolyte for next generation energy storage devices. So what, as a summary, what I want to say is, this DFT is not only applicable for pure crystalline or regular materials. One can use each and every type of materials up to a particular level. So here, people use that molecular dynamic simulation to get that conductivity, ionic conductivity on that polymeric system, and get that diffusion coefficient, and finally calculate some qualitative result of conductivity and compare experimental result. And, they obtain good result. But the first time that DFT based study, where we are just using that molecular mechanism and observing that interaction of salt with a polymer chain, as well as that the change in bond length, the change in breaking energy, and that creation of extra space to move that salt in between that polymer chain. This is observed, and this is good result, which will help to understand the mechanism of enhancement of ionic conductivity of different polymeric systems. So far, this is up to that solid polymer electrolytes. When that one salt is doped, further we can enhance this work when we insert in this polymer and that solid polymer electrolyte with this salt with some inert nanomaterial, just like silica type or ZRO type inert material, and we can observe. We will try to observe what the effect is saying, because in experimentalists are showing that when we use that inert particle, then conductivity enhanced. Sometimes it's 2 to 3 orders enhancement we are observed. So we will also see the effect of that inert particles in the structural part of this particular polymers. So thank you so much for Dr. team and Dr. Academy for financial support in this particular to organize this workshop. And I would like to show that so these are the papers. So this is introduction of PU with this density functional approach. This is a paper by B.K. Sharaw, Rachna, and published in Polymer Bulletin in this year. And second is the first principle study of PU with this silver iodide with in this chemical physics lecture. And now ab initio study of mechanism strength of solid polymeric chloride. And here that breaking the mechanical strength and breaking energy we have calculated for this system, and this has been published. And one paper is communicated by Sivani. So thank you all for hearing me with patience.
Okay. Okay, thank you, Dr. Verma sir, for sharing your expertise on the polymers study based on DFT. Now I request participants to share their queries. So there are some questions in the chat box by Jyotirmoy Dev sir and Yogita Chaudhary. Sir,
Okay, so thank you, Kulvinder, and some. Jyotirmadev, could we explain the details how HSAB principle is connected with carrier mobility? Sorry, dear, I cannot explain here. So you have to Google it. It is very good given in some books of chemistry as well as physics related to hence electrolytes. Why the morphology of polymer nanocomposite varies according to solvent. And I think I have covered this one when we use that salt and that thing. Then this is the preparation part, and experimental paper can give the answer. So kindly explain again HSAB. So please, you have to Google it. I'm sorry. Okay, this is just this is related to just positive. In chemistry, we have studied about that Lewis based principles and other things.
Any other questions related to DFT, polymeric studies, 2D materials, nanomaterials?
I think people are tired getting 14 and 15 continuously lectures and so many labs. So I will not further torture. Thank you all for hearing me, and you can mail me anytime. Definitely, I will answer. And the people who knows me, that I never take time to answer the reply in mail. So please, you can mail me. I am always ready to help the researcher and that beginners especially. Okay, thank you.
So sorry, there is one question by Kulvinder Singh. Please comment on potential applications of polymer semiconductor hybrids.
Actually, that polymer semiconductor hybrids materials are used in solar cell based devices now, right now. And various optoelectronic devices as well as electrochemical devices, people are using polymers separately as well as polymer semiconductor hybrids, and even some polymers which have semiconducting behavior are being used in solar cells. So in the theoretical part of study also that that semiconductor polymers are under study for optoelectronic devices.
Okay, thank you, sir. Any other question? Any other question with the participants related to any lab session or any theory session, sir? This is our last expert talk. So if you have any doubt regarding any lab theory session regarding DFT,
So in during labor, we
please,
can discuss.
Tanaya Dora is requested to please stop presenting. I think Miss Tanaya Dora, ma'am.
Okay,
So there is one more question.
one more question. The normally calculated band gap is between maxima and minima at k points, but can be measured in between maxima and minima of k points. What it means? We normally calculate the band gap in between maxima and minima at k points, but can be measured between maxima and minima at k point. So in I think you are talking about that wind plot. So in wind plot, some symmetry points are taken, and if the same symmetry points are taken, then it is measured as direct band gap. And different symmetry points are the gap in the different symmetry points are taken. That is indirect band gap. So generally, we take difference between two lines, which is above from that Fermi energy level, and second one is the below of that Fermi energy level, which we known as HOMO and LUMO type lines, and the difference is measured as a band gap.
Okay, thank you, sir. Any other questions? Or may I end this talk? Please be fast if you have any query. You can say on mic or type in the chat box. Okay, I think it's okay. So, okay, thank you, sir.
In any case of questions, you can mail me. My email ID is available with you. Okay, so you can just post me. Just don't hesitate. And hesitation, no need of hesitation. You can post any type of questions, and I will reply. Okay. Thank you.
Okay, thank you, sir, for sharing your expertise with us and sharing your valuable, you are very busy nowadays. So, for sharing your time with us, thank you.